So it's widely known by now that we use randomness in most areas of computer science, like algorithms, distributed computing, cryptography, to name a few. And in these applications, we typically require that the bits that we use are independent and uncorrelated. So in this direction, actually, there has been some work which showed that some basic cryptographic tasks are not possible even with almost random bits, where the bits are not totally independent and uniform, but maybe comes with some new entropy. Also, most of the randomized algorithms that we study assume that you have access to uniform uncorrelated strings. And finally, if we look at natural sources, most of the sources are not uniform, and typically they're very correlated, and a natural goal would be to use these natural sources to come up to actually extract purely random bits. So the question here is, how do we model a weak random source? So maybe a preliminary attempt would be just to say that the source has good Shannon entropy, where the Shannon entropy is defined to be the expectation of this log of 1 by probability of x equals to x, which is a good normalization. However, there is a problem with this notion of measuring the randomness of a source with the Shannon entropy. For example, let's just look at this distribution D, which with very high probability, so D is on n-bit strings, and with very high probability, it takes, with 0.99 probability, it takes just the string 0, all 0 string. And with probability 0.01, it's uniform on all the n bits. One cannot really hope to extract random bits from this source, but this has linear Shannon entropy. So to go around this, in the 1980s, a lot of researchers came up with this definition of Min-Entropy, which is sort of the worst case version of Shannon entropy, where you look at the support of x, this distribution x, and look at the place where x places the maximum weight on a string x. And that's sort of the minimum uncertainty that x has in its domain. And that, with this normalization, that's essentially Min-Entropy.
So this problem, this source is not so big, right? I can look at a few bits and see that I get non-zero, and then I know that I'm uniform.
Right, but these strings are really long strings.
So maybe it's not clear, maybe it's not clear, but what you would like is to generate a distribution that's statistically close to the uniform distribution. Since within distance epsilon to a uniform distribution, it would be impossible on any number of bits, on any number, or even on one bit, And this would be impossible if some string in the distribution, in the original distribution, has probability 0.99.
Because I'm not allowed to decide that, okay, I failed, I'm not generating.
Yeah, you're not. Yeah.
And you would not be told that this was the distribution.
Right. And and it's easy to check that this distribution D has very less Min-Entropy. Actually, it's order 1. So let's look a bit into this notion of Min-Entropy and develop some intuition. So let's suppose that x is on n bits, and it's a distribution. And we'll be dealing with n, k sources. So by n, k source, we mean a distribution on n bits with Min-Entropy at least k. And a special case is, say, when x is uniform on a set of size 2 power k. Then it's easy to check that this random variable has Min-Entropy exactly k. And by a founding work of Shor and Goldrick, in most typical applications, it's just enough to think of the special case, because in general, it can be shown that any n comma k source is a convex combination of these special sources. So in most arguments, this goes through. So for this talk, you can as well think of X to be uniform on some unspecified set of size 2 per k. All right. So randomness extractors are. Sorry. Yeah. Sure. Oh, sorry.
Anybody is not clear yet about the problem.
Yeah.
Somebody, generates a sample from X. You don't know X, and you want to use it somehow. So K may be square root n.
Yeah.
And you want to use it in order to generate maybe square root n completely random.
Right.
It's close to that.
Yeah.
So K is the square root n bits may be hidden in some square root n locations you don't know, or they can be just some 2 to the root n
right.
arbitrary strings.
Exactly. Yeah. Yeah. So yeah. And maybe for initial definition of an extractor would be a deterministic procedure which extracts uniform bits maybe from any n comma k source. Maybe this is what we want an extractor to do. So our goal would be we have a source x which we do not know. We just get a sample out of it, and we apply this extractor and maybe get a uniform or almost uniform bit. Right? So this may be called as a one source extractor. But by an easy argument, it can be shown that there cannot exist such a function. And I'll quickly go through the proof because it's a simple idea. Assume that there is such an extractor, ext, which extracts from any n comma n minus 1 source, say. And this extractor outputs zeros and ones, right? It's a deterministic function. So let's look at all the strings, all the n-bit strings on which the extractor outputs 0, put them in a set, and the remaining into another set. So by an averaging argument, at least one of them is of size at least 2 power n minus 1. So we can define our source x adversarially to be on the larger set and uniform on the larger set. So it has min-entropy at least, min-entropy n minus 1. And our extractor is identically either 0 or 1 on this source. So one cannot hope for a one source extractor. So how do we get past this difficulty? One way is maybe make assumptions on the weak source. In this direction, there has been a long line of work. There are bit fixing sources where you assume that there is a good subset of coordinates where each bit is independent and uniform. Or maybe look at affine sources where the weak source is actually a subspace, an affine subspace. Or samplable sources where the source is output by some reasonable model of computation, like polynomial size circuits. Another way is maybe without making assumptions, but access to more number of weak sources.
So in all those cases, like especially the last one, is there an extractor which doesn't use any randomness?
Yeah. For the samplable sources, yeah, there are for polynomial size circuits, there are some extractors. There are some impossibility results as well. But
you have to make assumptions.
Yeah.
Yeah. Yeah.
We're just trying to remember.
Yeah. There's Travisan. Yeah. Also for AC0 circuits, there are better known extractors. All right. So if we have access to more number of weak sources, there has been a really fruitful line of work here. This notion of seeded extractors, where it's assumed that you have a source x and a small uniform independent string, which is used to extract this randomness out of the weak source. And there are really good constructions known with beautiful work. But the focus of this talk will be where we have access to two independent weak sources. All right, let me quickly give you an outline of how this talk will go. So I'll introduce extractors, both seeded and two-source. and also present our results on two source extractors. And there's a very nice connection to Ramsey graphs. See, two source extractors, or in fact two source dispersers, can be interpreted as Ramsey graphs. So they give expressions of Ramsey graphs, so I'll talk on that. And for techniques, I'll be basically spending time on our construction of the two source extractor. So this has, on a very high level, two steps. One is using two independent sources to reduce it to some kind of generalized bit fixing sources. I'll get into that into more details later. And then extracting from such generalized bit fixing sources using things called as resilient functions. Again, I'll get into all these in later slides. And finally, some conclusions and open questions. All right, let's look at what a two-source extractor is. Let x comma y be independent n comma k sources. So recall that n comma k is a source on n bits with min entropy at least k. So you have x and y, and this extractor gets a sample from x, a sample from y, and it outputs a uniform bit or almost close to uniform bit. More formally, for simplicity, I'm just saying that it outputs one bit, but in general, the goal would be to output more bits. But for this talk, let's just, since our extractor just outputs one bit, so more formally, the probability that the output of the extractor is 1 is close to 1/2, where the probability is over the source x and y.
Why do you want just 1 bit and not k?
We actually want k bits, but in our paper we could just get 1 bit. But there has been a follow-up work which actually shows how to get k bits. But the definitions are easier when you just extract 1 bit. So, all right, and there is an easy matrix way of viewing a two-source extractor. So let n be 2 power n and let k be 2 power k. And the question now is to construct a Boolean n cross n matrix such that every k cross k submatrix almost contains equal number of zeros and ones. So essentially, each entry would be the output of the extractor. And
the matrix M is there.
yeah, right, yeah. It's the table of the extractor. Yeah.
So not just construct, but give efficient construction.
Efficient construction of that. Yeah. And existentially, it's known that you can do it for k as small as 2 log n. So, for example, we could just look at any subset of, say, 3 columns and 3 rows, and we would want the entries to be roughly balanced. And this should be true for any choice of your rows and columns. All right, let's look at what's been known for. Sorry, yeah, sure.
So existential, you mean there exists such matrices?
Yeah,
or
exactly.
in fact, random matrices.
Random matrices with high probability satisfying. Yeah.
Is there a lower bound?
I'm sorry?
Is there a lower bound? Or
Yeah.
Same.
It's the same. Yeah.
Well, up to constant, yeah. Half, 1/2.
It's a simple count.
But in this case, it's much.
Explicit constructions. This question of coming up with an explicit two-source extractor was asked parallelly by 2 papers, I think in Fox or Stock 85. So one was by Santa Fazirani and the other by Shore and Goldrick. And yeah, so probabilistically there exists two-source extractors for min entropy, log n plus a small constant factor.
it's not 2 log n?
No, so yeah.
Take another log.
Yeah. And for explicit constructions, let x and y have x have min entropy k1, y have min entropy k2. Then Shore and Goldrick, using the classical Lin's lemma, showed that the inner product function is an extractor for min entropies anything larger than 1/2. min-entropy rate, anything larger than 1/2. And after 20 years, Bourgain used sophisticated methods from additive combinatorics, some line point incidence theorems, to slightly better the bound from slightly larger than 0.5 to 0.5 minus a small universal constant. And Raz showed how to extract from two sources when one of them has slightly larger than 0.5 and min-entropy, and the other source can have actually logarithmic min-entropy. And our main result here is an explicit two-source extractor for polylogarithmic min-entropy. And for large enough n, the constant c can be taken to be 75. And there has been a follow-up work by Meka which improves slightly one of our components, and this can be taken to be 10 now. All right. So, and another follow-up work by Shinley has shown how to extract almost all of the randomness out of the extractor, and this builds upon our construction. So another thing is our extractor has polynomially small error, so that's one direction where we hope future work will get it to exponentially small error. All right. So before getting into techniques, let's look at what Ramsey graphs are, because two-source extractors can be naturally interpreted as Ramsey graphs. A K-Ramsey graph on n vertices is essentially a graph with no independent set or clique of size k. And the bipartite version is where the bipartite graph has no subgraph, so no subgraph, which is the complete k cross k bipartite subgraph, or the empty graph. And again, the existential result shows that you have really good Ramsey graphs. And an open question which has attracted some attention is coming up with explicit constructions of such Ramsey graphs. And a quick illustration of what a Ramsey graph would look like. So you have all this, so you have the complete k cross k graph, and you're maybe coloring each edge either green or orange, and you want that for any choice of your subsets on the left and the right, the edges between them are not monochromatic. All right, and there has been, sorry, yeah, sure.
So the only difference from extractor here is that you don't care that the edges are balanced. You just care that
Exactly,
they
yeah.
are not all red and not all.
Yeah, it's a weaker property than, yeah.
And the adjacency matrix of the of this graph
Is again the,
M
yeah, right.
I'm just asking questions because nobody else is asking.
All right, and there has been a long line of work on constructing explicit Ramsey graphs. I'll quickly get you through all these parameters. So the top one is the existential result, and the Linz lemma again shows that the Hadamard matrix is a bipartite, gives you a bipartite Ramsey graph with k square root n. And there has been quite a few works on constructing Ramsey graphs which are not bipartite. So using intersection theorems, Frankel and Wilson in the 80s, now using some using epsilon by spaces in a clever way. Grolmusch again using intersection theorems, Barak by graph products. I'm sorry?
I have some construction.
Oh, I'm sorry. Yeah, I think I need to upgrade that list. And Gopalan provided a general framework. So all these constructions get stuck at this 2 power omega of root log n bound. And Parikshit Gopalan actually provided some explanation as to why this was the case, because all of these constructions used in some way the polynomial representation of the OR function.
Wait, what did he provide explanation for?
So for a long time, most people were trying to get below the 2 power root log n bound, but it was stuck at there. And he showed that if we get below this using these techniques, that's essentially proving some stronger degree bounds on the symmetric representation of the OR function.
Which is impossible.
Which is not, which is considered to be a difficult problem.
Oh, it's open.
Yeah, it's open. Yeah. And Pudlak and Rodel slightly improved the bound for the bipartite Ramsey graphs. And then by breakthrough works of Barak, Kindler, Shaltiel, Surakov, and Wigderson, and a follow-up by Barak, Rao, Shaltiel, and Wigderson, really good constructions of Ramsey graphs were known, which actually breaks the Frankel-Wilson bound. And in recent independent work by Cohen, we have bipartite Ramsey graphs for which achieve the bound 2 per poly log n, and our result essentially matches the bound obtained by Cohen up to constants.
So question, with 3 sources, was everything easy? Just 2 was hard?
Yeah, for 3 sources, it's not easy, but there is a recent Fox paper which, yeah,
Before that was multiple.
yeah, yeah,
So
yeah,
4, what was
yeah,
A decade of work slowly
After
gets to
yeah.
For extractor, because for 3 or more, at some point you have something called the stepping up lemma for Ramsey.
I think,
So then it should, that should be easier.
yeah.
Maybe for 4.
I think for constant number of sources, I think Avi with Barak, and they had this using sum product theorems. They showed how to do it, and then for 3, I think Rao had constructions which handle linear min entropy for one of them and polylogarithmic is small for the other. But for the stepping up lemma, I'm not sure.
This would be just Ramsey, maybe not.
Yeah, maybe not. Yeah, I think you're right. Yeah.
But then it's much less than log. It should be like log log, log log log.
I see.
So there
Yeah.
are like you can there is a coloring of 3 uniform complete hypergraph with no by 4 corners.
I see.
With no,
Right.
yeah, but maybe it's not.
With 2 colors. Yeah.
Oh.
Yeah. Yeah. For the disperser problem, maybe it's yeah.
So is the bipartite case very different from the non-bipartite? Is it easier?
The bipartite case actually is the tougher problem because it implies the non-bipartite with similar bounds.
the non-bipartite, I mean, the symmetric case requires the matrix extractor to be symmetric. So,
Right,
I
yeah.
mean, not the extractor, the set
The set.
you are looking for. This K by K submatrix is principal in the standard Ramsey problem. So in the bipartite case, there are more demands. All submatrices which are K by K, not just principal.
Right. Yeah. Now let's look at the techniques that we use in our work. So I'll introduce some of the tools that we use. So one thing that we use a lot of times are strong-seeded extractors. So a strong-seeded extractor takes in an input, a weak source on n bits, d uniformly random independent bits, and outputs m bits such that the output is statistically close to uniform. And this approximation epsilon means that the statistical distance between the 2 distributions is at most epsilon, and the string um is independent of y. And there are really good constructions known by work over the last 2 decades where d can be as small as order log n over epsilon, and we can get most of the min entropy out of the source X.
So one interpretation of this is that there are polynomially many functions
Right.
that, for every source, almost all of them are good.
Yeah, exactly. So we'll use this property that almost, so what this essentially says is that for most seeds Y, the output of the extractor is close to uniform. And we'll also use the notion of resilient functions. So let's look at what a q comma epsilon resilient function is. So we'll call a function f to be q comma epsilon resilient if for any choice of q coordinates.
Wait a minute, these are functions on what, on n bits?
Yeah. Oh, okay. Yeah. So f is a Boolean function on n bits, and what the property that we want out of f is that for any choice of q coordinates, if we sample the coordinates outside uniformly, then the probability that f is already not determined is at most epsilon. Let's look at an example to probably make this clearer. So for example, parity is q comma 1 resilient. So what this means is that even if you choose just one coordinate and uniformly sample the other coordinates, this coordinate can still influence the function. Yeah, so the probability that it's not fixed is, oh, it's, yeah, oh, sorry, it's fixed is, yeah, sorry, yeah. Yeah, it's not fixed is at least 1 minus epsilon. Yeah, sorry, yeah. Okay, sorry, yeah, sorry about that confusion. So the probability that f is not fixed is, yeah, I think that, yeah, this is right, yeah. Right, yeah, sorry, yeah.
So if you fix q coordinates,
So
then you sample the rest.
you sample the rest, and you want your f to be,
You don't fix them, you fix the,
yeah,
the location.
You fix the location.
Location,
Yeah.
you just look at some q coordinates, the first q coordinates, you randomly plug inputs.
for the
other
outside.
one, and you want it not to be a constant. You want the restricted function not to be a constant.
So you sample that.
You sample that, and you want this function to be fixed with probability at least 1 minus epsilon.
Not fit, you want it probability at least epsilon. So you have to change it most here to constant, then it's correct.
Do you want it to be constant or?
Yeah, we want it to be constant. Yeah, we want it to be constant.
You want it to be non-constant, right?
No. So what you can, yeah, you can think of these as the bad guys, the q coordinates. And
I mean, the parity is q1 resilient, so your epsilon is 1. Parity indeed is not fixed with probability at least 1, right? It's not
I see, yeah, there's some confusion with the wording, but yeah,
So you better clarify it.
yeah, yeah.
No, I think it just said most should be at least. That's what I said.
Yeah, okay, yeah.
So we repeat it, or you want to demonstrate it on majority.
Okay, so what we want essentially is, I'll just use the blackboard here. So we want a function f from 0, 1. So we have this set of coordinates and say, so let q be a subset of n, and the size of q is q, right? And what we want is the probability that f, when q bar is sampled uniformly, is fixed, is at least 1 minus epsilon.
It is fixed, is it most?
No. So this q are the set of bad guys.
So q are
For parity, does parity satisfy that thing?
So for parity, even if this Q has one bit, then, oh, I see, it should be 0, yeah. Yeah. So even if Q has one coordinate, then the probability that F is not fixed is 1, right? So epsilon should be 0 there. That's the confusion I see.
So again, what you wrote now, you wanted the probability that it is fixed is smaller, not that it is big, right?
No, we want it to be big.
The probability is 0, which is greater than or equal to 1 minus 1 still, right?
You wanted it
So
You don't want Q to affect the election.
yeah,
So I think, yeah, exactly. Noga, so you think Q is, this is an election.
This is an election.
F is the outcome of an election.
Yeah.
Everybody outside of Q is choosing their vote randomly. They vote randomly, and you want that the vote of the bad guys, Q, which are allowed to choose
Yeah.
their votes
You don't-
later,
yeah.
not to influence.
you don't want them to bias it towards one of them. So essentially, it's saying that small coalitions cannot bias the function.
That's right.
Yeah.
So you want that if the other guys are voting, then the function is not fixed.
No,
It is fixed.
Otherwise, the other guys could determine it. Yeah. You don't want Q to determine.
Right. Yeah.
The point is that somehow saying that
With
something
parity,
is
it
one
is never
zero.
fixed.
Yeah, exactly. Yeah.
Parity is a really bad.
It's a bad example.
Not
Yeah.
resilient.
Yeah.
Because even
One player can actually influence it, right? Yeah. 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 And a majority is a good function for coalitions of size slightly less than square root n. So is this clear?
I think what should have been the first line in the example is not what's written, but the parity is not QT resilient for any Q positive and T less than 1. That would be basically what should have been on the first line of the example.
Yeah, probably, yeah. All right. Okay, so great. Let's start with a preliminary attempt of maybe constructing a two-source extractor. So let's use these explicit constructions of seeded extractors which just outputs one bit, and take a weak source X, and run this extractor on all of its seeds. So recall that the length of the seed is polylogarithmic, so actually for epsilon to be chosen to be, say, polynomially small, the length of this z prime is polynomial in n.
So what is the prime? Oh,
It's
you want the extractor on every possible seed.
on every possible seed, yeah. So we get a sample from X and run the extractor on every possible seed, and since the output of the extractor is just one bit, so each bit corresponds to a seed,
So what do you want to construct now?
a two-source extractor.
You have two seeds. Two is the seed.
No. So we have two sources, X and Y. We just take the first source, take a sample from the first source, and run a seeded extractor on all of its seeds with this sample.
So you don't use the second.
No, we don't. Till now, we don't use the seconds. Yeah. And by the property of the strong seeded extractor, almost 1 minus epsilon fraction of these bits are close to uniform.
So green is uniform. And red
Yeah, green is uniform, and the red are the non-uniform bits.
But the uniform is individual.
Yeah, it's individually uniform.
Just,
Yeah.
They may be very correlated.
Yeah,
but
yeah,
Every green one is good.
Yeah. Yeah, and 1 minus epsilon fraction of the bits are uniform, but they need not be independent, as we pointed out. And the bad bits may depend upon the values of the good bits. So, I mean, we could probably try to say that since there are lots of good bits, maybe majority gives us a bit which is good. But yeah, this does not work because the uniform bits are arbitrarily correlated, so we do not really know what's going on.
So it can be that all the green ones are 1 together, or they're all 0 together.
That's not,
That would not be so bad for majority.
yeah, that cannot be possible since I guess each bit can take just one min-entropy out of x, but yeah. But since the source is of polynomially small length, so I mean at most k of this can have min-entropy. So okay. The second attempt is to make to get more structure into these uniform bits, make them almost t-wise independent. So one could potentially try to maybe make all the good bits to be uniform and independent, but that's not possible since we do not have so much min-entropy. It's a polynomially large source. So all right. So this step, we'll use this tool which is called as a t-non-malleable extractor. I'll not really get into what this is. And this is a recent work that I have with Vipul Goel and Shinley, which gives non-malleable extractors for polylogarithmic min-entropy. And now this works that if we take a sample from X, run the non-malleable extractor on all its seeds, then actually a good fraction of the bits are uniform and also t-wise independent.
What should we think of t?
So think of t as polylogarithmic.
Okay, so every log or polylog of the
Yeah.
green guys
Of the green guys are t-wise. Yeah. So it's strictly not. So it's actually almost t-wise independent. But for this talk, let's think of it as t-wise independent. And maybe we could try now to apply the majority function because of the. So majority is known to have good properties even for bounded independence. Seed length of the non-malleable extractor actually gives the length of z prime to be quasi-polynomial in n.
So far you don't use it all the second extractor? Or
Yeah, till the second source. No, not till now. Yeah.
will arrive
It will arrive, but yeah. Yeah.
because it's impossible.
Yeah. Okay. So yeah, but still this does not work out because you can actually show that it's not possible to get such good non-malleable extractors such that the number of bad bits are less than square root d. So we cannot really apply the majority function. Also, there are more issues like the error gets pretty large. So yeah, and this is sorry.
It just says that you showed it with one source, you cannot do it.
Yeah, exactly. This is not surprising since we just have one source. Yeah. Yeah. All right. So our approach, very high level idea is in step 1, we use x and y, both the sources now, to construct a string z, which is polynomially large d bits, such that there are d power 1 minus delta bad bits. And the good bits are almost polylog-wise independent.
So the number of red guys will be like d to the 0.9.
Yeah, d to the 0.9. Yeah.
It will not be an epsilon factor. It will be much smaller than an epsilon factor.
Yeah.
This is essential.
Right. And if we could get that to maybe less than 0.5, then we could directly apply the majority function. But our technique, we can actually it's possible to show that it's not possible using our technique at least. And step 2 is an explicit function which outputs 1 bit and extracts from the source C. So essentially after step 1, we forget about these two sources and just think about this bit fixing source with t-wise independence. All right, so for executing step 1, we have the source x, and again we use the non-malleable extractor, run it on all the seeds. So this is okay. So yeah, we run it on all the seeds. Now the crucial idea is to sample a small subset of coordinates from this large string z prime using the second source y. So using the second source y, we'll project this large string z prime onto some coordinates which are polynomial in n, but it's not as large as n power t. And a very well-known way of choosing a pseudorandom subset is again using seeded extractors, and this was first used by Zuckerman in 97. So the pseudorandom subset of coordinates would be take your second source y, run it on all the seeds, and now this extractor is not a non-malleable extractor. It's just a seeded extractor. So your m is actually polynomial in n. And z would be z prime projected onto t. So we interpret each of this as a number in 1 through d. So the output of the seeded extractor is actually log of capital D bits. So
the purpose is only compression.
Yeah.
Have
right.
a super polynomial number of bits, and you want a polynomial number of bits.
We need a polynomial number of bits. Yeah.
So you need
Yeah.
to use the other source just
Yeah.
to select this sum.
Exactly. Yeah. And we want that the fraction of good bits is roughly preserved.
But wait, what are R1 for M?
So R1 through Rm are short seeds which the seeded extractor uses. So we run the seeded extractor ext on all its seeds.
All is.
Yeah. But since it's a seeded extractor, it has much better seed length. So
So here the bad bits are still a positive fraction.
yeah. And the number of bad bits now is, so initially z prime had epsilon fraction of bad bits, and now this extractor adds an error of epsilon prime. So the fraction of bad bits is epsilon plus epsilon prime times m. And it's possible to set parameters such that this is bounded by some m power 1 minus delta for a small enough delta. So our new string z prime, sorry, the new string z is on m bits, and it has m power 1 minus delta bad bits, and the rest of the bits are t-wise independent, where t is polylog m.
How big was D?
D was,
Quasi-polynomial.
yeah,
It was quasi.
D was quasi-polynomial.
How big was T?
Sorry, t is polynomial.
No, a little
You mean m?
Well, it is
D is
polylog.
2 to the poly in T.
Oh, t is polylog n.
is polylog.
Yeah, 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 yeah. So one thing is compression, and the other is if you actually look at the errors, then yeah. So it's very crucial to actually pseudorandomly do this, because since the bits are not t-wise independent but close to t-wise independent, so there's a so if it's gamma close to t-wise independent, then there's a lemma which says that it's gamma times size of the string power t close to a t-wise independent distribution. So to manage with the errors, it's important to do this step.
So
Yeah.
this is the only use of the second source.
Yeah.
Just to compress.
Yeah, exactly. Yeah. So
It's a very benign use. It seems
Yeah.
like an
Yeah.
overkill.
yeah, exactly.
Maybe you can do it with 1.5 sources.
Yeah, so yeah, our extractor is actually strong in the second source, because this is the only step we use. So for most choices of the strings of the second source, the output is uniform.
Do you need also less min-entropy in the second source?
I mean, no, so yeah, we still need, yeah.
But it's strong in the second source. This you could get without loss of generality for any extractor.
Oh, I see, by Boas-Baruch's argument you're saying.
Kind of an easy.
Yeah, so I think the construction, so the argument there needed really small error for the extractor, is that right? Yeah. So, yeah. I mean, our extractor has polynomially small error, so yeah, I think I checked that, but yeah, but still. All right, and a slight modification of a construction by Shinley in his 3-source extractor can be used to get similar parameters. No, so now we'll execute step 2, where we have a string z with m bits. Number of bad bits are m power 1 minus delta, and the good bits are polylog wise independent.
So now blue is good and white is bad.
Yeah.
So where do you get the independence? Polylog wise?
Oh, that's the black box use of the non-malleable extractor.
Can you say a little bit more?
Okay. So our first step was running this non-malleable extractor with this string x and over all its seeds. So a non-malleable extractor has this nice property that it's a stronger version of a seeded extractor, where it says that if you take a string x, a seed y, and also look at the output of this non-malleable extractor on t other choices of your seed. So basically, you allow an adversary to pick any t functions and tamper the seed, like apply this function on the seed. And now look at the output of the non-malleable extractor on all these things, right? So non-malleable extractor of x, s1, non-malleable extractor of x, f1 of s1 through non-malleable extractor x, ft of s1. So you want this joint distribution to be close to uniform. Sorry, at least the first bit to be close to uniform, given the other things. And this should hold for most seeds. So this is the definition of a non-malleable extractor. And by a recent work, we actually constructed such extractors for polylog min-entropy, which is crucial in this application.
You can take this to be the definition of non-malleable extractor. Just one. So in a normal seeded extractor, what you want is that except for a few bad seeds, every seed gives you a uniform output. In non-malleable extractor for parameter t, what you want is that there's a few bad seeds, and then every choice of t other ones, t good ones, give you joint independence.
Right, yeah, exactly, yeah.
It's a more even though non-malleable started from cryptography, that's the cryptographic connotation.
Yeah.
This is the
Yeah. Right. Yeah. All right. Thanks. Any more? All right. So now the blue bits correspond to the good bits, which are t-wise independent, and the white bits are the bad bits, which may depend arbitrarily on the good bits. Because if they do not depend on the good bits, we could just take parity, right? And let D be the t-wise independent distribution on the good bits. So our idea is to maybe construct a function which may be a circuit, which outputs one bit and is almost balanced for all such sources Z. So which is essentially an extractor. So the thing we are concerned with is how much influence does this set of bad bits have on C. So for this, we look at this, that what's the probability that when the good bits are chosen from this t-wise independent distribution, that the probability C is not fixed. So this essentially is the quantity which shows the amount of influence that the bad guys have on the function C. All right. A sub-step is actually saying that we can just solve an easier problem where the good bits are just not t-wise independent, but actually uniform and independent. But for this, we need some good properties out of the extractor C. If the extractor C has some nice properties, then it's enough to just assume that the good bits are uniform and independent. So here, the crucial idea is this, that if the extractor C is a monotone function, then it's easy to check if the bad guys are actually able to change the function C for some fixing of the good bits to x.
So you are explaining now why you can assume
Yeah,
that they are all
yeah,
uniform.
yeah, exactly, yeah. So one property that we need, I'm saying, is that C is monotone. Why is that? Because if C is monotone, let's fix the good guys to x. Then this circuit C prime, which checks if C of the good guy is set to x and the bad guy is set to 0, and the good guy is set to x and the bad guy is set to 1. If they are different, since it's monotone, if they're not different, it implies that the bad guys could not influence this function C, right? So yeah, in general, this is a hard problem, but if C is monotone, then there's we can just add one more depth to the circuit C and we get this function C prime. So the probability that C of x is not fixed is equal to the probability that C prime is 1.
This has nothing to do yet with the uniform versus T-wise. This is just
No, this is just an observation.
yeah,
Yeah,
so it's analytic. You are going to explain why
Right,
uniform
yeah.
is enough. This is not why this is
Yeah.
another
yeah, exactly.
good thing to
Yeah,
have,
yeah.
which is
It
not
w-
explained.
Yeah. So this and another property will actually get us there. Yeah. And now we'll use. Now the idea is this, that we have this nice result from pseudo-randomness, which is actually a breakthrough result by Braverman, which says that if C is in AC0 of small depth, then the bias of, so if C is in AC0, then we can easily check that C prime is also in AC0 with slightly larger depth. Then the bias of C prime is preserved under D and the uniform distribution. And this was proved by Braverman. And all we need is polylog-wise independence for a large enough constant. So what this shows is that if C is in AC0 and monotone, then the probability that C of C is not fixed when the good bits are from the uniform distribution and when the good bits are from the T-wise independent distribution is close, right?
If you could construct a resilient function which is monotone and AC0,
Yeah, exactly.
then it will
Yeah.
What's the problem with constructing a constant function as a resilient function?
Sorry, can you?
If you just take the constant function,
Yeah.
it's
So
resilient.
right. Yeah, that's a very good question. So we want the function to also be almost balanced. Yeah. Because we want an extract. Yeah. 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 Actually, we spend most of our time showing its balance. So. Yeah. All right. So if we have such an extractor, then we can assume that the good bits are independent and uniform. So to recap, we want such a resilient function and which is also unbiased.
What is the almost unbiased property?
It's when you actually want to prove that the probability that your function takes probability 1 is close to half, then you use the bias of the function. Right, right.
So what's the output is just the output of C?
Yeah, the output is just the output of C. So you would want probability that C of Z is 1 is close to half. And then you'll use that it has low resilience and is also unbiased.
Low resilience, did you train that?
Yeah, it's a simple probability lemma which shows that you can actually fix these bits and then use that as.
He's asking a
Oh.
more basic question. You want low resilience because
Oh.
only the good bits are uniform. The
Yeah.
bad bits are arbitrary. You don't know what they are. They are correlated.
Oh,
with
I
the
see.
good bits.
Yeah.
So you should think of them as this set Q.
Which is
It's
trying
not
to.
supposed to influence what the
Yeah.
good
I see.
bits
So
are.
first you show it's a good extractor on Q,
No.
or you show it's unbiased?
No, no, no.
So so if it's unbiased, then what we'll show is that since it's also resilient, the bad players cannot push the bias too much, right? So it's an extractor. Yeah. And we construct such a function by de-randomizing a construction of Chattopadhyay lineal from 1990. And their construction is probabilistic, and they show that the constructor sample space of n per order n square functions such that it's n by log square n resilient. And let me quickly describe what the Atay lineal functions are. So a tribes is a partition into tribes, and each tribe, and the function is 1 if there is unanimously a 1 from any one of the tribes, right? So that if we take ands of the tribes and then an or. And the Atay lineal function is an and of n such tribes where each tribe is on a randomly chosen partition of n. So the blocks of the partition you can think of as ordered log n. Actually, it's log n minus log n. And also these tribes are, some of the variables are randomly negated, so this sample space is actually not monotone. And the resilience is n by log square n.
It's already constant depth, it's depth 3.
Yeah, it's a depth 3 circuit here. So the problems, naive de-randomization takes n per order n square time, which is not good enough, and it's also not monotone. So our effort here is essentially de-randomizing Atay lineal and also making it monotone. And one key ingredient is actually coming up with an explicit construction of these partitions. So in tomorrow's talk, I'll get into much more details on this part. So the properties that we want are that for any subset T of n, it has small intersection with most partitions. And what I mean by an intersection with a partition is that it has small intersection with any block of the partition. And this is used to bound the influence of the function. And also we want that the partitions are pairwise seed random, which means that if you pick any two partitions, take any two blocks from these partitions, they have bounded intersection. And this is used to bound the bias of the function. And we actually get this collection of partitions using, again, seeded extractors. So seeded extractors can be seen as, in a graph theoretic way, that you have a sample x, and you output an embed string, and there is an edge if there is a seed which gets x to that output. So all nodes on your left has degree 2 power d, where d is the seed length. And further, it has this nice property that for most choices of your x on the left, the neighborhood of x intersects any subset t in the right fraction, the fraction that you would expect if it's randomly chosen. So if bad is all those x for which, say, its neighborhood intersects t in slightly larger than its density, then there's a theorem by Zuckerman which shows that the number of bad such x is bounded by k, where this seeded extractor works for min-entropy k and has error epsilon. And the idea is somehow to use this to come up with partitions, even though it's not directly clear. So the way to do it is, I mean, this is a very high level idea. So think of n as, say, m times b. For b is small. And suppose we have a collection of subsets of size b each of this form, 1, I1, 2, I2 through b, IB. Right? So you can think of this as a box. And suppose Si looks like this. So using this, we can actually think of Si as a block in a partition and shift Si to get all the different blocks of your partition.
B is about low.
Yeah. So by shifting, this naturally corresponds to a partition. So each of these SIs can be used to get a partition. And the way we define these SIs is actually the neighborhoods of each of these inputs x. All right, and to quickly recap, so the properties that we needed were that for any small subset, it did not intersect too many of the partitions in a large way. So this translates into a similar extractor property here for this definition of the partitions, and using the property that I mentioned, that most x's intersect in the right way, this can be proved. And further, we want that any shifts of the neighborhoods of two distinct x and x prime do not intersect in a large way. So this corresponds to the partitions being pseudo-random, that is, any two blocks of the partitions do not have large intersection. So we actually show that a construction of Trevisan satisfies these both properties. So the first property, the second property, actually a simpler version where ij are zeros, was proved by Shin in 2012. So we show that the Trevisan extractor actually has these nice properties. So this can be actually used to get a collection of partitions. So some ingredients in the analysis. So we analyze the bias of the modified Hatay lineal function in a new way, and this is crucial for getting monotonicity and also showing that these partitions work. And a useful inequality, which I'll just mention and conclude, is Jansen's inequality, which was very useful for us. So
Where do you have probability?
yeah. Oh.
Where is the probability?
Oh, so yeah. So the so yeah, we actually use Jansen to show that the function is unbiased, almost unbiased. So
You take like
Yeah.
uniform input to the
yeah. So if S1 through STs are subsets of R, think of SIs as small. And if and suppose we construct the set T where each element R in R is picked with some probability P for, say, a small p. Now, if the SIs are small and each have low pairwise intersection, then we can say that there is some kind of independence going on. So what we can say is that the probability that none of the SIs are